In today's lesson, we are going to review atomic structure. Based on your previous courses in science and in learning chemistry, you are already aware that the atom contains 3 subatomic particles. These particles are the proton, the neutron, and the electron. The location of each of these 3 subatomic particles are important to know. The proton and the neutron are both found in the nucleus, and we now know through Niels Bohr's discoveries that the electrons are found in energy levels that surround the nucleus. You also should be aware of the charge of each of these subatomic particles. Protons are positively charged, and we use this notation to indicate the short form of it. Neutrons are neutral, there's no short form there. Electrons are negatively charged, so we often write a negative sign with a VE to indicate negative charge on the electron. One thing that you may not be aware of are the masses. And relative mass indicates, what is the mass when you compare the proton and the neutron and the electron to each other. And so what you notice is that the proton and the neutron each have 1 AMU, okay, so right down here, AMU stands for atomic mass units. This indicates that both the proton and the neutron have the exact same mass. However, the electron is 2,000 times lighter in mass. And that's important because when we look at the atomic masses of our elements on the periodic table, the electron is not factored in to those masses in any way. Standard atomic notation is used to represent the basic information of elements on the periodic table. X refers to the symbol of your element. And then there are 2 values that are usually listed to the left of your symbol. And the upper value refers to the mass number or the atomic mass, and the lower number refers to the atomic number. Both of these you can find on your periodic table. If we set up an example of this using one of our elements on the periodic table, so for example, if we looked at calcium, we would write calcium symbol down as we look it up on the periodic table. And then you need the atomic mass or the mass number of calcium plus the atomic number. When you look at the mass number of calcium on the periodic table, you're going to notice that it is a decimal value. So it'll say 40.08 AMU. And when we write this down, we never write that full value. We round the mass number. So because it is 40.08, we would round down. If the mass is 40.5 or greater, we would round it up. So in this case, we round down and then we write the atomic number for calcium, which is 20. So this would be the standard atomic notation for calcium. What do these values mean? Well, the atomic number, okay, which is the lower number of your element, is the number of protons in the nucleus of an element. And this is also equal to the number of electrons if it is a neutral element. Okay, if it's not a neutral element, then it is called an ion. We're going to be getting to those in a few lessons. And then you cannot say that the electrons and the protons are equal. But for now, we're going to assume that it is a neutral element. The mass number, which is the upper value, is the mass that is held in the nucleus of the atom. We learned this from Rutherford's experiment, that all the mass is held in the nucleus. The mass number equals the mass of the protons and the neutrons, so they are added up together. We represent the structure of an atom by drawing Bohr-Rutherford diagrams. And the name of these diagrams come from the 2 scientists that contributed major discoveries to the structure of the atom. Bohr, who came up with the energy levels where electrons sit, Rutherford, who is credited with discovering the nucleus. So here are 2 examples of Bohr-Rutherford diagrams, and it says, which element do these Bohr-Rutherford diagrams represent? Stop the video, take a look at the periodic table, and determine which element each of these represents. Once you have figured this out, we will now go over the identity of each of those elements and how you would determine that. The easiest way to determine is to look at the number of protons that are sitting in the nucleus of your atom. You know that the number of protons, by definition, is the atomic number of your element. So who is number 9 on the periodic table? Well, this would be fluorine. And who is number 11 on the periodic table? Well, that would be sodium. And the number of neutrons can also come and go. We're going to learn about that in another lesson. But the easiest way to identify these atoms or these elements is based on their atomic number. Notice that the electrons are placed around the nucleus in the pattern that we learned in the previous lesson. In our first energy level, so right here, our first energy level, we can fit 2 electrons. In our second energy level, we can fit 8 electrons. And in our third energy level, we can also fit 8 electrons, although sometimes we may not need all of those electrons. And if you look at each of these, especially in sodium, you don't have enough electrons in sodium to fill up that third energy level. But when you count up all of your electrons, they should equal the number of protons as long as your element is neutral. The outer electrons in any Bohr-Rutherford diagram are called valence electrons of our elements. And while it's good to know this, many times we don't need to actually draw an entire Bohr-Rutherford diagram to carry out things that we need to do in senior chemistry. Many times we are just concerned with those valence electrons. So those valence electrons are in that outer energy level of your element. And when we represent the number of valence electrons of an element, we draw what we call a Lewis structure or a Lewis diagram. And it's a very easy way to figure out the number of valence electrons that most elements have. You could either draw the Bohr-Rutherford diagram, but sometimes that takes a little bit more time than you need. A better way is just to go to your periodic table and to look at the group number. Now, the group numbers right here for the transition metals, they do not apply. Okay, so these elements, we do not apply to this Lewis structures trend. But if you look at the rest of them, here's group number 1, 2, and then we skip over to group number 13, 14, 15, 16, 17, 18, and so on. Now, when we look at the elements that go underneath each of these group numbers, all of them have the same number of valence electrons. So everybody in group 1 has 1 valence electron. Everybody in group 2 has 2 valence electrons. And we can prove that by drawing the Bohr-Rutherford diagram and counting up the electrons in that outer energy level. When you get over to the other side of the periodic table here, everyone in group 13 does not have 13 valence electrons. At the moment, you think that the maximum you can put in an energy level are 8 electrons. But what they do have is we just sort of get rid of the 1 in front. They have 3 valence electrons. Everybody in group 14 has 4 valence electrons. Everybody in group 16 has 6 valence electrons, and so on. Now let's do an example of putting all of this together. So we have potassium as our element to do an example with, and we're going to write the atomic notation for potassium, calculate the subatomic particles, and then draw a Bohr-Rutherford diagram and a Lewis structure for this element. So you head over to your periodic table and you look up the position of potassium and specifically the atomic mass and the atomic number of potassium. Potassium's symbol is K. Okay, K is used because that is the Latin name of potassium, which is kalium. Starts with a K. And when you look up the atomic mass, it is 39.10. So we're just going around to 39. And when you look up the atomic number of potassium, It is 19. We want to calculate the number of subatomic particles. So we'll just do that below. And I always start with the number of protons. That's the short form that I use. Then we'll do the number of electrons, and then we will calculate the number of neutrons. So remember that the number of protons is equal to the atomic number. The atomic number is 19. And for now, we're assuming that our elements are neutral, which means my number of negative electrons has to equal the number of positive protons, and that would also be 19. To figure out neutrons, remember that the atomic mass is equal to the number of protons and neutrons. So what will happen here is that in order to get the number of neutrons, I have to take the atomic mass and subtract off the atomic number, and I get a value of 20. Sometimes the neutrons equal the protons and the electrons, but most of the times it doesn't. You have to do a subtraction to figure out the number of neutrons. We were also asked to draw a Bohr-Rutherford diagram and also to come up with the Lewis structure. So let's start with the Bohr-Rutherford diagram. So we'll just box this off, and then we'll draw our Bohr-Rutherford diagram. We start with our nucleus. So we draw our nucleus, and we have to put information in about our nucleus. So we know that the element is potassium, and we put the symbol of potassium in the nucleus, including the subatomic particles that sit in there. So the two particles that sit in the nucleus are your protons, and so we write 19 positives, and then neutrons, and so we write in there 20 neutrons. I'm squishing that in, but you get the idea. We know that our electrons sit in energy levels that surround the nucleus. So we start placing them into these energy levels. So in energy level 1, I can fit 2 electrons. So I have 2 down and 17 to go. In energy level 2, I can fit 8 electrons. And when we place our electrons in energy level 2, we start with a single at the top, then another single at the side, a single at the bottom, and then a single at the other side for a total of 4. Then if we need more electrons, and we do, we go and pair them up next to all of the singles that were there for a total of 8. We cannot go above 8. So I currently have 10 electrons. I need 9 more. I move into energy level 3, and I place again single electrons. So that's 14, 15, 16, 17, 18, and I need 19. I got to go into energy level 4, and then I'll put that 19th electron at the top. If I need a Lewis structure, again, I only look at the outer energy level. Okay, so outer level equals valence electrons, and I only have 1 valence electron. So for my Lewis structure, all I do is I write the symbol of my element, and then I put the 1 electron, 1 valence electron around the symbol. Okay, so in this case, I put it at the top. If you wanted to put it to the side, that would be perfectly acceptable, but you only need 1 valence electron because that's all you've got in the outer energy level.